All right, so you're back with us again, ready to dive into some cutting-edge machine learning research. Buckle up, because today we're going deep into a paper that's causing quite a stir. Rethinking Diffusion Model in High Dimension.
By Zengxin Zeng and Zengxin Zeng.
You got it. This paper's tackling some pretty fundamental questions about diffusion models, those incredible AI systems that are pumping out hyper-realistic images, music, you name it. You've seen the results, they're everywhere.
And they're only getting better, which is really exciting to see.
But here's the thing, this paper's asking if maybe, just maybe, we've been thinking about how these models work all wrong. The classic assumption is they're learning the super complex statistical rules of the data they're trained on.
Like some sort of master probability map of all the possibilities, right?
Exactly. But what if it's not that complicated? What if, especially in these high-dimensional spaces where data gets really spread out, diffusion models are actually relying on a much simpler trick?
That's a pretty bold claim, especially given how powerful these models have become.
Oh, absolutely. This deep dive, we're going to unpack the paper's arguments, see how they reached this conclusion, and even explore some potential implications. Might even spark some novel notions for future research. Who knows?
Should be a wild ride. I'm definitely ready to jump in.
So the paper kicks off. Right off the bat, they're acknowledging the amazing things diffusion models can do, particularly with images. It's hard to deny the results.
Yeah, generating high-fidelity, diverse images, it's almost like magic sometimes.
Right. But then they point out that all the current ways we explain this magic, all these different mathematical frameworks for diffusion models.
Markov chains, score-based models with their SDEs, even the newer flow matching approach.
They all rely on this assumption that the model's learning the full probability distribution of the data. But in high dimensions, with data points scattered all over the place, that just feels
implausible, maybe? Like, how could a model truly grasp all those subtle relationships in such a vast, sparse space?
It's a head-scratcher, right? Traditional machine learning tells us that's a tough problem, learning complex distributions in high dimensions. So, the authors lay out their mission. Figure out if diffusion models are really doing what we thought they were doing, or if something else is going on.
And they're not messing around. They lay out a pretty ambitious set of contributions. They analyze how sparsity affects the model's objective function. Then, based on that, they propose a new way to interpret what that objective function is actually achieving.
And they don't stop there. They introduce this natural inference framework, which, get this, it can explain a whole bunch of different existing inference methods all under one roof.
That's really impressive. Unifying those different techniques is a big deal.
Oh yeah, it's unifying DDPM, DDIM, even those advanced solvers like DPM solver, all within this framework. And from that, they even propose a brand new inference method that might just be more efficient than what we have now.
A lot to unpack there. Maybe we should start with the basics. The paper does a good job of explaining the forward diffusion process.
Right, the part where you take clean data, like an image, and gradually inject noise into it, step by step.
Over time, the signal, the original image, gets weaker and weaker until it's almost pure noise. They show the math behind this, how the noise gets mixed in, both for Markov chain-like models and for flow matching.
And the important thing is, regardless of the specific math, the goal is to drown that signal and noise.
Exactly. And then comes the learning part. They explain the objective for each main type of diffusion model. Markov chain-based models, they're trying to learn how to go back one step in the noising process.
Basically, predict a slightly less noisy version.
Yep. Score-based models, they're learning the score of the data distribution at each noise level. This score tells you the direction of increasing probability.
And for flow matching, it's learning this velocity field that guides the noisy data back towards the clean data.
Now, what's super interesting is they point out that all these different learning goals, they're all mathematically linked to predicting the mean of the original clean data given the noisy version.
So instead of having these separate, seemingly unrelated objectives, they're actually all getting at the same thing.
Exactly. And they formally prove that predicting this posterior mean, it's the same as predicting the original data itself. This becomes super important later on.
Okay, so now we get to the heart of the matter. How data sparsity affects what the model is learning. They remind us that the big goal is to estimate the average of all possible clean data points that could lead to a given noisy data point.
Makes sense. But in practice, we can't look at all possible noisy data points, right? So we have to sample them.
And that's where ancestral sampling comes in. You pick a clean data point from your training set and add noise to it following the diffusion process.
Makes sense. And then they get into the mathematical nitty-gritty of the posterior distribution, the probability of clean data given noisy data. If your training data is a bunch of distinct samples, which it always is in practice, this posterior becomes a bunch of probabilities assigned to each of those samples.
Each original training sample gets a probability based on how far it is from the center of the noisy data point. The closer it is, the higher the probability.
This brings us to the big idea. Weighted sum degradation. In a high-dimensional space, if one training sample happens to be much closer to the noisy data point than all the others,
That single closest sample basically dominates the whole average. All the other samples further away, their contributions become tiny. It's like trying to hear a whisper in a hurricane.
that's a great analogy. And to show that this actually happens, they do some quantitative analysis on ImageNet, ImageNet 256 and ImageNet 512 to be precise.
These are huge image data sets, and they're looking at the latent space, which is a compressed representation of those images. Even compressed, it's still high dimensional.
They look at how often this weighted sum degradation happens and how often the posterior mean just becomes the original clean sample they use to create the noisy input.
They do this across different noise levels and for different noise schedules, VP and flow matching.
And the results are pretty stark. The degradation gets worse as the noise level decreases, which means as we get closer to generating the final image.
Flow matching seems more susceptible to this than VP, and the higher the dimension, the worse it gets. Below a certain noise level, the model is basically just pointing back to a single training example a lot of the time.
So if the model's spending so much time just predicting the closest sample instead of learning the full, complex probability distribution, maybe our understanding of how these models work needs an update.
Right. They propose a simpler interpretation. In these high-dimensional, sparse scenarios, the model's mainly learning to reverse the noise and predict the original signal. It's not about mastering probabilities, it's about denoising.
This leads to a really cool analogy with image frequencies. An image, most of the important stuff is in the lower frequencies, the shapes and colors. Fine details are in the higher frequencies.
Gaussian noise, the type used in diffusion models, it spreads across all frequencies equally. So when you mix an image with noise, those fine details are the first to go.
Training a model to predict the original image from the noisy one, it's like filtering out the noise and trying to recover those lost frequencies.
And the model seems to learn to prioritize the lower frequencies first, which matches how diffusion models generate images, starting with blurry shapes and then adding details.
It's a much more intuitive way to think about it. And this leads to the next big question. Can we understand the inference process, how new data is generated, in a similarly straightforward way?
They say yes, and that's where their natural inference framework comes in. It basically says generating a new data point is a series of steps where the model predicts the original, clean data. Each prediction takes a combination of previous predictions and the noisy data as input.
They also introduced this self-guidance idea, which is similar to classifier free guidance, where you guide the generation based on a class label.
Or even like unsharp masking in image processing, where you enhance edges by subtracting a blurred version from the original.
In their framework, self-guidance means combining an earlier, less refined prediction with a later, more refined one to get a better result. They have fore, mid, and back self-guidance based on how much weight you give to the earlier versus later predictions.
And here's the elegance. They show that any linear combination of two predictions is just self-guidance with a scaling factor. This means the whole inference process, all those prediction and refinement steps, can be represented as a single matrix.
The numbers in this matrix tell you how much weight to give to each previous prediction step to get the final result. And the really cool part is they demonstrate that all these different inference methods, from DDPM to DDIM to even the advanced solvers for SDEs,
And flow matching samplers too.
they can all be represented as specific ways of setting up this matrix in their framework. They derive the equivalent weights for the clean signal and the noise for each method. It's a unifying view of all these different techniques.
And this brings some clarity. It shows consistency between training and generation. Both involve predicting clean data.
Yeah.
It makes inference visually understandable.
And importantly, it reveals that the sampling algorithms we use are just specific configurations within this broader framework.
Maybe they're not the only or even the best way to do things.
Right. And they explain why some samplers are better than others. The faster, higher-order samplers often have negative values in their matrices, which corresponds to that fore self-guidance, and that seems really good at enhancing image quality quickly.
On the flip side, simpler, lower-order samplers with their mid self-guidance using positive coefficients, They're more robust when you crank up classifier-free guidance.
They even show how you can tweak the matrix to control how sharp the generated image is. Pretty neat.
And if inference is all about this matrix, what if we design even better matrices? They optimize these weights and get higher image quality in fewer steps than existing methods, at least on CFAR10.
Their optimized matrices prioritize recent predictions and use force self-guidance early on for fast convergence.
But they also notice this over-enhancement phenomenon. Apply too many refinement steps or use really strong self-guidance, and you get weird artifacts.
They think it's because of a mismatch in fine details between training data and generated samples. Fine-tuning the model on its own over-enhanced outputs helps.
But they're clear that the optimal matrix isn't one size fits all. It depends on the model and what you want. This opens up possibilities for automating the search for good settings, or even using a small neural network to learn how to refine predictions step by step.
This research has huge implications. More efficient inference means lower costs and faster generation times, making these models more practical for all sorts of applications.
Controlling image sharpness gives us more flexibility. And this deeper understanding could lead to even better diffusion models in the future.
Absolutely. All right, time for novel notions. I'm thinking, what about adaptive self-guidance via reinforcement learning?
Ooh, interesting. So instead of fixed parameters, we trained a little RL agent to adjust the self-guidance parameters at each step based on the generated samples quality.
It could get feedback from an automated metric or even human input. The reward could be based on image quality, guiding the agent to find the best parameter sequence. RL has been used to optimize models before. Why not the inference process itself?
We could get generation that adapts to the data and desired characteristics in a more nuanced way than static methods. It might even learn to avoid that over-enhancement issue.
Another idea, building on the sparsity findings. Hybrid objective functions leveraging sparsity insights. If the model's not learning from the full distribution in sparse areas, maybe we design a loss function that considers that.
A loss that dynamically shifts focus or combines the usual weighted sum with something that encourages learning from nearby samples when the data is sparse. We could use density estimation or nearest neighbor methods during training to figure out the data sparsity.
A hybrid objective could make models more robust and efficient with sparse data, maybe needing less data or training steps to achieve the same performance. It could bridge the gap between the mathematical ideal and the reality of sparse data sets.
Lots of potential there. So the takeaway here is that diffusion models might be working in a simpler way than we thought, especially in high dimensions. It's about reversing noise and predicting the original signal.
And the natural inference framework gives us a powerful new lens to view and improve these models.
The weighted sum degradation idea really makes you rethink what's being learned. And the possibilities from natural inference, faster sampling, more control over the output, it's exciting stuff.
Absolutely. Anyone who wants to dive deeper, the link to the paper is in the show notes.
Definitely check it out. And as always, let us know what you think, what questions you have. Thanks for joining the deep dive.
See you next time.
Until then.